So 15 years ago, I heard a wonderful anecdote, which I never thought would be applicable to me. So imagine that there was an election in a very respected Academy of Sciences, like Australian Academy of Science, and then, by lo and behold, the pure mathematician was elected. And the chairperson invites him to deliver a talk about the work of his life and gives him 10 minutes. And the person goes like that, and how am I supposed to do that in 10 or 15 minutes? And chairperson looked at him and said, "Speak very slowly." I will follow the advice, and I will speak very, very slowly. So, imagine that we live in a one-dimensional world. Then all mathematics which was invented in 15th, 16th, and 17th century will suffice. All of you studied the calculus in school. Well, at least I think that your age is such that you really did study. Nowadays, I'm not even, I don't know what is now happening in the school. So, but you certainly studied calculus. You studied classical calculus of one real variable. So you know what is the function of one real variable. You could differentiate this function, so you could find this differential. You could integrate it. And all of that would suffice for all needs of physics if we were living in one-dimensional world. Because momentum, impulse, distance traveled, velocity could be computed by using these means. The real change started about 100 years ago when quantum mechanics came into the fore. That's, of course, linked first and foremost with the names like Heisenberg and von Neumann. That was realized in 1930s, or maybe circa around 1930s, 1920s, something like this, that in fact we live not in a one-dimensional world. Oh, well, that's also sort of a trivial thing what I'm now saying. However, it was realized that the micro world and the real geometry of this universe is completely unclear. It is not necessarily three-dimensional, four-dimensional. Nobody really knows. The real geometry of the micro world and the university as a whole is still the great mystery. At the time, there was come to the understanding, there was perfect mathematical apparatus developed called Hilbert spaces, which is infinite dimensional analog of our three-dimensional space. That was an absolute change in the paradigm of thinking, that instead of one-dimensional variable, we now have something what are called operators. To give you the feeling the word operator mean, think about the matrix. This matrices you also studied in school. This is just rectangular arrays, and this is the first simplest manifestation of the operator acting in, say, in three-dimensional space. Every 3x3 matrix filled with a complex of real numbers, that's a manifestation of operator acting in three-dimensional space. That's what happened at the time, and from that moment, the development of new mathematical disciplines, which are called non-commutative analysis, non-commutative geometry, non-commutative probability, really started. So I will explain in my talk, at least I will try to explain this change of the paradigm in this thinking and what actually I am and my group doing at the University of New South Wales. So how I will do this? Of course, I will be appealing in this audience mostly consisting of physicists, chemists, medical people, biologists, to some other parts of science. And the first time in my life, I'm producing mathematical talk without single formula. So science knows a lot about ideal crystals, knows how electric conduction is done, the heat equations, how heat expands in those crystals. However, in the reality, most crystals have a variety of defects. This was topic which was very hot in the solid body physics in 1940s, 1950s. So suppose you have an ideal crystal with some impurities, with some defects in that. How will you then measure the free energy which appears from those defects? How you will measure and understand the properties of this new crystal with those defects? That was a proper solid body physics. And the mathematical methods which were developed for that are called perturbation theory. What is the perturbation theory? What is the word perturbation? That's when you have some object and you perturb it a little bit. This comes, I hope that you will see some analogy with the classical calculus. So how you will look at those derivations of the functions. You have a functions of, say, real variable, then you a little bit perturb this variable. And then you study the new function. So, for example, you take the divided difference and compute the derivative. Exactly those things happens also in the perturbation theory. Only now you perturb not one single number, but you perturb an operator. You perturb an operator with some other operator. And then for this perturbed operator, you compute the same quantities which in the classical one-dimensional mathematics you would be computing. You will try to differentiate this function. You will try to find some other properties which will be measuring the properties of these ideal crystals. My work is perfectly related to this area, and that's where the word non-commutative analysis comes. If you wish, you can call it non-commutative calculus. However, I prefer the word analysis, a little bit more scientific. So this is where the non-commutativity really manifests, and this part of science is still thriving, and we are still working a lot, producing the results to this matter. Another example which immediately also comes to mind, so I said that the perturbation theory was thriving in 1940s and 60s and so on. However, if we remember the Nobel Prize in Physics in 2010 for the development of and discovery of graphene, and measuring the magnetic properties of the electron gas through this graphene, believe me, this work, if to express it in mathematical terms, is a perfect example of the perturbation theory, and perfectly relates also to the mathematics which we developed as well. So this was a little bit about non-commutative analysis. Now, how to approach non-commutative geometry? Well, there are several examples which I'm going to put on the slides, and one of those belongs to Sir Roger Penrose. He was a mathematical physicist and also the real physicist, not just mathematical physicist, real physicist and mathematician, and he came up with the idea how one can tile the plane aperiodically. So if you look at this picture, then you will see that the whole plane is actually tiled using just pieces of two sides. And no pattern will ever appear. No pattern. So you could not say that you can, say, divide the plane in two parts or in four parts, and those parts will be similar to each other. No, it's not going to be the case. There's always difference, always. So symmetricity, in a way, this is also another expression of commutativity. Everything what is symmetric is more or less. Of course, I'm lying through my teeth, but nevertheless, this is the light. This is the right ideology. That symmetricity is somewhat similar to the commutativity. There is no commutativity here. This pattern is aperiodic. It never repeats itself. Of course, Penrose was motivated by different questions and different ideology. However, he came up with this beautiful object, which has been studied very intensively mathematically. Okay, so this is a beautiful tiling, and now since we're talking about diversity, I could not really help but put another slide. I'm from the part of the world which is Central Asia, Uzbekistan, Tashkent, and well, you can see on the picture here a beautiful example of Middle Eastern architecture when the people discovered those tilings about 500 or 600 years before. Penrose. So also probably motivated because in Islam they could not really follow the patterns which are symmetrical. So I grew up looking at those pictures and similar pictures. Actually, I'm lying. It is Alhambra in Spain, but nevertheless, never let the truth stand in the way of a good story. It's still similar through all Eastern world, in particular in Uzbekistan. And those ideas were really, really present in architecture, in art and science. And well, lo and behold, in 2011, Nobel Prize in Chemistry was awarded for the discovery of the quasi-crystals. What are those quasi-crystals? Periodic tilings are the mathematical models for those quasi-crystals, which appear also in the nature in a very, very natural way. So it is three-dimensional version, if you wish, those quasi-crystals, three-dimensional version of those aperiodic tiles by the Penrose. So you could ask, what is the connection? What is the connection? The connection is linked with the name of Alan Kohn, the Fields medalist in 1980s from France, probably the greatest mathematician of the last century. He developed the so-called non-commutative geometry. Alan Kohn was mostly motivated to come up with a proper mathematical apparatus to see what is happening in the very fine structures in the micro world, because actually nobody really believes that the geometry of the micro world is described in the acceptable terms, like we used to use the word manifold, or Riemannian manifold, to describe those orbits of the electrons and manifolds at which is driving. He came up with the ideas and ideology mostly, producing the extraordinarily influential book called Noncommutative Geometry, which allows us to view those non-commutative manifolds which do not really consist of the points in space, but which allows to compute certain geometrical characteristics of those manifolds, to see how we can not how we can visualize them, but how we can compute something about them. That story of non-commutative geometry was partly successful because there was certainly certain applications to physics, and partly not that successful. Oh, very quickly now. So what is non-commutativity? In the one-dimensional world, we have two numbers always commute. So we take the product, and 3 times 4, it is 4 times 3. In the real world, when we do the operations and operators, they do not commute. If you look, for example, at this slide, then you look at these two operators, R1 and R2. So this is the anticlockwise rotation around X and around Z. And if you do them in different order, you have 2 completely different results. If you look here and here, you can see completely different results. So you see, in the real world, non-commutativity is present. It is not like, as I said, in a one-dimensional world. And the last thing, which of course I'm late, because I was speaking very slowly, is a non-commutative probability. Imagine the matrix like this, 10 by 10, filled with the absolutely arbitrary colors. This is, again, the matrix, non-commutative object. How we will be studying the property of the huge ensembles of those matrices. All ideology, all these questions come from physics. Physics linked to the name of Eugen Wigner, 1950s, and which are still all of those subjects which I just listed, analysis, probability, and geometry, are linked inextricably, and this is the main topic of my study. Thank you very much.
Thank you, Fedor. Any questions or comments? So in terms of mathematics, quasi-crystals have been predicted, but experimentalists have taken a long time to really even accept, even after discovery, that quasi-crystals are not really acceptable, like even famous scientists like Linus Pauling. But the mathematicians have already predicted quasi-crystals long time back?
The fact of the matter that all those ideas were developed intrinsically in mathematics long before they were really needed. And this fact, well, the majority of mathematicians is accepted as a proof that they really needed, that they are something what was really required for the development of quantum physics. And that this is not the only possible approach. This is not the only possible approach, but I still think it's the most successful.
Okay, Susan Scott there.
So do you think that Roger Penrose and Alain Kohn should have shared in the Nobel Prize for quasicrystals? Because I have a bit of inside information on that story.
Well, I have a huge respect to both, so I will reserve my opinion on that. No, it is unpredictable. I think that I'm a huge fan of Alain Kohn, and when I was talking to physicists, somebody told me like that the 20th century left the names of Einstein and Riemann. So the whole Einstein physics was done in the Riemann geometry. 21st century will leave only one name, Alain Kohn. The jury is out. We'll see. I'm not sure. As calculus, the real calculus development took 400 years before it came to the fruition. Maybe non-commutative geometry will also take a few hundred years before we see the real result of it. Although, as I said, there are real results also. There are solutions of different problems. There are this explanation of quantum Hall effects, which is done precisely in terms of non-commutative geometry, which I really admire. But, Nobel Prize, it's a bit political thing, so I would
on that note,
I will side of
okay, could you please join me to thank Fedor for the interesting talk?